Yes, guys. So today we will see this rule 4. We already covered R1 dot R2, R1 plus R2. So now this next rule says that if you have a language and this language is represented by FA, let's say this is FA1, and this is and when we say FA, so for sure we are talking about a regular language, and this language is also represented by a regular expression, and let's say we call that R1. And now if someone asks you, can you please find the clean star property of this regular expression? So what does it mean? They are interested to find R1 star. If you do that thing, if you apply the clean closure property or clean star property, which is the same name which is the two different names of the same thing, it means that the resultant thing will be also, it will be a universal set, but still it will not change the behavior of the language, and it will remain regular language, and it can be represented by R1 star. And it is possible to draw the FA of that, and that FA will also be the clean closure property of, of this thing, and we can say that this is FA2. So this will be a new language. R1 is not equal to R1 star, but once you apply the clean star or R1, you will get a new language, which will be um which for sure it will be infinite language. Okay, and it can be represented by FA, and that will be FA2. So this is basically what we are saying. So if R is a regular language, regular expression, and this regular expression is for this language FA1, and now you want to find the R star of that, it can be represented by FA2. And this is also, regardless, this will be a universal set, but still it will be a regular language. So this infinity will not change the behavior of this language. Okay? So this is what basically what we are saying. And how we do that, we need to create a we need to see that with one practical example, like we did two examples last time, and we will see now uh, another example based on the same rules, two tables, and we can see that how we do this. Okay, so let's say we have this language, uh, and this language is basically, this is an FA, and now if you see that this FA has three final states, one start state, all edges are letter by letter, and there is no, you can say, word any on any label. So this is, and it is taking care of garbage collection, so it means that this is a valid FA. Okay, and now if you see that one of its start state, its start state is also a final state, it means that this language has ability, this FA has ability to accept lambda also as a word in this language, because we learn this rule that whenever you have a start state and it will be a final state, what does it mean? It will accept lambda, because you always start from the start state, and when you start from the start state, you are not giving any input, and it means that you are standing on the start state, and without giving any input, you are on the final state also. And it means that it allows you to accept the lambda there. So this is basically idea behind that. Now we need to, we are interested to find the, and this is and if someone asks you what is the, what is this language, so now we need to see that what is this language, what is the regular expression of this. So this language will, because of this, it will accept lambda, and it will also accept if from here to here, and it will accept one a, and that will be a valid word, or as many a's, that will be a valid word. It can accept a word which can end with b because of this. It will never accept a word which will start with b. You see, when it goes here, there is no way to it comes out from this state. And when you have the 1b, after that, if you provide, let's say a b, after that, if you write either 1a or 1b or something, anything, it will not accept that. Okay, so this is this language. And now if we, because of this thorough uh, analysis of this FA, we come to this conclusion that from this part to this part, we need to get A star. If we get A star, this will help us to get lambda because of star property, and 1A or as many A's. And then after that, because of this, you might have uh, A 1A, and then uh, A star, because if you see this, if you start from here, A star, B. Okay, and that's it. This is the regular expression for this language. And now this is our one regular language which has this regular expression, and this regular expression is represented by this valid FA. Okay, very good. Now so guys, whenever you lost anywhere, please ask me a question, okay? Do not wait that I will finish. You can interrupt me anytime. This is very important concept. Riley, could this also be, I like that you talk, but you're right. Could this also be lambda plus, okay, so Riley, if you, we do not need to write lambda exclusively, because when you have A star, so it has implicitly, it means that it has lambda there. So you can get lambda from A star. We have plus here. So plus means either you can choose this or this. And if you wanna get lambda, you can get lambda from A star. But if you just put, but if what I understand by your message, that is, it can be something like, it can be, it be something like this, if you are talking about that, and then this is not good, this is wrong, because this way you will not get only A. Because if you see my this machine, you start from here, you reach here, you have just one letter A, it will be accepted. But by this, you will not get only A. By this, you will not get two A's, three A's, because this will give you guarantee that this A and this B must be there. So this thing, this set, you will not get from this regular expression. Okay, so this is not good. So that's why we not write only lambda with that, but we want to write lambda, and we achieve lambda by this way of writing. So we write this thing. Okay, that's good.
I just have a quick question.
Yes, please.
So the A star is just from the second final state? Just the,
Yes, for A star will cover these two states, because if we see what is the set of A star, so A star is equal to lambda A A. Yes. And now, if you see our start state is a final state, we can get lambda from this A star. If you just stop here, but if you have one A, you can come here. You have 2A, one round, 3A, second round, fourth round. So this will cover, A star will cover these two states. Make sense?
Yeah, it does.
Okay, that's great. So now we are saying that, um, this is good. This is what we have. This we are happy with this. Now we are interested to find, and this is what? This is our regular expression. Yes, this is our regular expression. And now I want to find the clean star of this whole thing. I want to see that what will be its equivalent FA. Because this FA just cover this. I want to find clean star of this whole thing. So it means I am interested to find clean star of this. I want to see that what is that language look like, how that FA look like, and what will be how mainly we are more interested to find the FA of that. Okay. So now to do that, we need to do the same job. We need to draw two tables. Okay. And then we need to fill both tables parallel. And then we want to see here. So in this case, uh, in this example, actually, we are lucky that our start state is a final state. Okay? But you know one thing, let's say I have a language which will only accept two letters, A and AA. Okay? And now I am asking you, can you please find the S star of that? So can you please help me to write the S star of that? Anyone? What will be the first letter of this language? So initially, so I have my language which has just two words, A and AA, and I am interested to find the S star of that. So what will be the first word? Anyone? Jacob Morris. Jacob Morris, are you there? Yes.
Yes.
So what will be the first word of this language? If I have S is equal to A comma AA, and I'm asking you to find the clean star of that, so what should be the first word of this language?
With the A.
Uh, okay, and go ahead.
I'm not sure what the second one would be.
Okay, so the first word, as if you see the message from Riley, he mentioned that the lambda. So we always start from the smallest thing. Lambda will be the first word, and then A, and then A, and then combination of all these three words. So two, four A's, 2A, 3A. So this will be the, so mainly lambda will be there. So what I want to say that regardless you have lambda in S or not, S star will have a lambda. This is what we learn in clean closure property. So in this example, you have your start state is a final state. Let's say your start state does not have a final state. Let's say, just for example, that we have this example and this plus is not there. Let's say, okay. Then what happened? So we need to figure out our first state Z1, and what is the start state here is X1, because we have only one machine. Uh, and this is Z1 is the start state. Regardless, your start state is final state or not. When you take your Z1 must be a final state, because you know that when you apply clean closure property, so it will have one word lambda, and lambda only possible when your start state is a final state. So in this scenario, luckily your start state is final state, but just assume I gave you a question. In that question, I ask you find R1 star of this language, and your start state is not a final state. So even then, your Z1 will be a final state because this is the rule here. Okay, and I wrote this thing here. The language defined by R star must always contain the null word, so the start state must be the final state. Okay, so this is something. Okay, uh, we always uh, find what happen if you are at this at particular state and you get A as input and then B as input. So I last time someone asked this question that can we possibly check first B. So let's do this time. We check instead of A and B, we check B and A. So it will not change. It will not have any impact on the final result. Final result will same whether you first check A or you first check B. Okay, so it has no problem with that. But just for to make sure that we can do this way also. So let's do one example by this way. Instead of checking B A B, we check B A. Okay. So now our start state is x1, and this is also a final state. Now we are saying that what happen if you are at x1 and you have b as input. If you have b as input, you go here to x4. So we write this thing here, x4. Okay, we do not have this state before, and we will say this is a new state. This is z2. So if you are at z1, which is start and the final state, and you have B as input, you go to Z2. What happens if you are at Z1, which is X1, and you receive A as input? When you receive A as input, you reach to X2. Okay, we don't have this combination before. Now this is another, now we need to understand this thing. Whenever you reach to the final state of this machine, you never know that your word finish or it is continue. So you always consider the start state of this machine. Always consider. So you reach to the final state, you always consider the start state also with that. So whenever you reach to x2, you always consider the start state x1 also with that. Okay. So we don't have this combination before. This is Z3. And any one is final, your Z will be final. So X2 is final here. So any one is final. So Z3 will be final. Okay? And now we can say that when you are at Z1 and you receive A as input, you go to Z3. So we check this X1 for A and B. Any question here how we did this? Are we good? Okay. So now we need to see the second state, Z2. And we are saying that when you are at x4 and you receive B as input, so you see here when you are at x4, you receive B as input, you stay at x4, you receive A as input, you stay at x4. So it means that you will be at the same state, and it is x4, which is not a final state, and we already have the name of this state Z2 there. So we do not write give this state a new name. So we will say that this will be Z2, Z2. Make sense? And now we check this z2 also for 2 times. And now we check z3 for b and a. So we are saying when you are at x2 and you receive b as input. When you are at x2, you receive b as input, you will go to x3. X3 is what? Final state. And we learned that whenever you encounter the final state, you always write the start state with that. So which is x1. And now we check this x1 of z3. What happens if you are at x1 and you receive b as input? If you receive b as input, you go to x4. We don't have this combination before, we call this z4. Any one is final, z4 is final. And here x1 and x3 both are final. So your z4 is final. You are saying in case of b, you go to z4. Now we need to see z3 for BA. If you are at x2, you receive A, what happened? x2A, it will stay there. It is x2. And x2 is a final state. We need to write x1 also with that. What happens if you are at x1 and you receive A as input? You go to x2. x2 is a final state. We need to write x1 also with that. We don't write duplicate states. x2, x1, we already have this combination before z3. Okay, so now you check this also for A and B. It's better that, yeah, this is good. So now, because there's a limited space, so I don't write this. Now we are saying that let's check the Z4. For A and B. So you need to check individually x3, x1, x4 for A and B. First check x3 for A and B. So x3 for B. You are at x3 and you receive B, you go to x4. x4 is a normal state, so we will just write x4. When you are at x1, you receive B, you go to x4. You are at x4, you receive B, you stay there at x4. You don't write duplicate states. x4 already we use that, which is z2. So we don't need to write it here. You can show your work, but I have limited space. I don't want to go to the next page, so that's why I am deleting. But if you want to keep it, it has no problem with that. Now we need to see what happens if you are at x3 and you receive A as input. x3A will take you to x4. x1A will take you to x2. x2 is final. We must write x1 with that, the start state. x4A will stay you at x4. We don't write duplicate terms. x4, x2, x1. We don't have this combination before. We will say this will be z5. Any one is final, z5 is final. And here you have x2 and x1 both are final, so z5 is final. In case of A, it will be z5. And we check this also now. And now we go here for z5. We check A and B. So when you are at x4, you receive B, you stay at X4. X2B will take you to X3. X3 is final. You must write X1 with that. And you are at X1, you receive B, you go to X4. We don't write duplicate terms. X4, we don't have this combination before, this is first time. This is Z6. Anyone is final, Z6 will be final. And 3 and 1 is final. So now we check Z5 for A. You are at X4, you receive A, you will stay at X4. You are at X2, you receive A, you stay at X2. X2 is a final, you go to X1. You need to write X1 also with that. You are at X1, you receive A, X1 with that. We do not write duplicate terms. Z5. So we check this for A and B. Okay. Now we need to see Z6. You are at X4, you receive B, you stay at X4. X3B will take you to X4. X1B will take you to X4. You don't write duplicate terms. X4 already there, which is Z2. Don't need to write this. Okay. You need to check this for A. X4A will be at X4. X3A will take you to X4. X1A will take you to X2. X2 is a final state. You need to write X1 with that. And don't write the duplicate terms. So 421 is already there, which is Z5. So we don't need to write this. Check this for A and B. And after this, our new states are finished. This will stop this process. We will draw the machine according to this diagram, according to this table. Okay. So draw machine. Draw FA according to this. And this FA will be the clean star of the previous machine. And whatever I did, whatever I explain, I write this word by word here. So you can see all this thing is here. So when you go, you will read. So it is here. So this will those states. So you will not lost. According, and this will be, look at this one. This is the regular expression of this one. And this machine is R star of this machine. That's it. Any question, guys, here?
Where is the Z6? I didn't see that in the diagram.
We don't have Z6 there. Then really I don't have Z6. 1, 2, 3, 4, 5, 4, 2, 1, 4, 3. Oh, sorry, we don't have Z6 because if you see 4. So I made mistake. It's very good. You guys find these things. Okay, so if you see this, Z6 is 431. 431, so it is same thing. So I should not write Z6 here. So wherever I write Z6, I should write Z4. I believe that once you've done that, so then it will finish. Then you don't need to go to next step and delete this. Okay. So mistakes do happen. This shows. But now we are good. So it is Z5. So only thing is that I consider one state two times. That is a mistake. We should not because 1, 3, 4, 4, 3, 1 ordering does not matter here. If you have that states there in that combination, it is the same thing. So instead of writing Z6, we don't write the same state name two times. So that was a mistake, and we just correct it, and now we are good. So Z1 to Z5. Get this. Okay. And now if see we can counter verification of this. So let's say Z1, if you have B and A, B will take you to Z2. Let's draw this. So Z1, B will take you to Z2, A will take you to Z2, B will take you to Z2 means self loop. A will take you to same here, so self loop. Z3, B will take you to Z4. A will take you to Z3, self loop. Z4, B will take you to Z2. And A will take you to Z5. And Z5, B will take you to Z4. A will be self loop. It should be something like this. So now let's see this. You see, it is exactly the same thing. Z4 and Z5. This is what we did. So this is good. So any question, guys? All good. Very good. Then example two. Uh, Again, the same thing. You need to do this by yourself. So just draw the table and draw the regular expression of that. And according to that new table, you draw the machine. And this is the, in good English, the algorithm written here that how we do this, how we did this. I mean, in more concise way, you will see what I just explained. It is written here. This is again another example. Let's see what is this FA. So this FA is basically words with an odd number of B's. So it starts with A, it can start with B, and it will always, it can end with B also. It can end with A also because B and A. But if it has B, it has always odd number of B's. Means 1, then 2, 3, 4, 5, 6, 7. So always odd number of B's. If it has B's, that's it. It can have as many A's as many B's. So then this is again a new FA. If you want to apply R star on that, so you will get something like this. So that's basically some examples, but you need to do this in complete detail. You need to draw the table. So now, if I ask you these questions in exam, and you do not draw these tables, and somehow for some blessing you come to the final diagram, and I will not give you any single point. It will be zero. Please do not see YouTube videos for this thing. Uh, Somehow people merge both table in one table. I will not consider that, at least for this course. Please follow my method. This is not my method. This is the method I'm using. I'm following from the book, which is your textbook. Once you pass this course and you learn this and you will be expert of that, then I don't care you choose any short method. But at least for the learning purpose, I need to see your work, how you did this. I expect if I ask you these kind of questions in exam, I want to see both tables separate and the diagram. If anything is missing, I will not give you any single point of this. Okay? So this is very clear now. Now we want to see this thing, non-deterministic FA. I told you uh, that we have an FA and what. So here we finish our this topic. So now the new topic start. NFA. So what is NFA? So we saw FA, and we know when we did that, I explained you that FA, it is basically its name is complete name is DFA. What is D? Deterministic. Yeah, deterministic. Finite automata. What does it mean? It means that your FA is deterministic. It does not have, it takes care of garbage collection. It, every state should have two outgoing edges. If your summation is equal to A, B, so then two outgoing edges for A and B, it can handle that way. Okay, this is what is the definition of FA. So now, so far, you see that you can represent a regular language by regular expression, by FA, and by TG. Now, this is the another way of representing the regular language, which is called NFA, non-deterministic finite automata. So, what is this definition? So, non-deterministic FA is something which is in between FA and TG. It has some properties inherited from FA, some properties inherited from TG. It is not TG, it is not FA. So I mean it is not FA. It is more relaxed than NFA. Okay, DFA. It is more relaxed than normal FA or DFA. What is the whatever the name of that? Now, let me see that what are the properties of that. So let's see the definition. It says non-deterministic FA is a finite set of states. Okay, we have this also before. One of which is designated as the start state. Again, we FA also have only one start state, NFA also has only one start state. So this is good. So this is exactly how your FA is. Some, maybe none, of which are designated the final state. So there is no change in this first definition. Whatever FA, whatever NFA, they both are same. That it may not have any final state, it may have one final state, it may have more than one final state. Okay? And then it says that an alphabet summation of input letters. So it also has letter by letter. Again, the same thing. A finite set of transitions that show how to go to a new state for some pairs of state and letter. So it does not take care of garbage collection. So it does not take care of garbage collection. Okay, so this is basically what does it mean. So it means that we will see this line after. I will come back to this line. Let's see the diagram of this. So we have this machine. This is not FA, because if you see this, if you are here and you receive, sorry, if you are here and you receive B as input, you are not handling that. You are not taking care of garbage collection. And you are here and A, and then it is A also here. This is not the case with FA. FA, whenever you are at the one state, if you have A or B, there is always one path, either go here for A or B goes here. You will never see that from one state there are more than two outgoing edges. You will always see distinct two outgoing edges. If there is one, it is A, and the second, which is B. A, B, A, B, A, B, A, B. This is your FA. But here now, if you see that, it says A and B and A. So non-deterministic. If you are here and you receive A, machine will not able to make a decision by itself. It can go right on this side or it can go right on this side, because it both are taking care of A. So which ride is good? Machine cannot make decision by itself. So this is non-deterministic approach. So when you have a room and you have two doors, you cannot predict that from which door someone can come in. So this is non-deterministic. If you have only one door, you can say always people will come from this door. This is deterministic. We don't need to be figure out and guess, or this time someone will come from this door or this door. So this is not deterministic. Deterministic, always one behavior. So FA, NFA is non-deterministic. But another thing you see, it has strictly one start state. Final state, we don't care. May have one, may have more than one. Another thing, it can be, it can have always letter on their edges. You will never see a word here. You will never see a word here. Always letter by letter, exactly the way FA behave. Okay, so now this is your NFA. So it's kind of FA but more relaxed. So you can say that how it is more relaxed. It can have non-deterministic thing and no, don't take care of garbage collection. Beside everything same, whatever FA is doing. And now if I am interested to write the regular expression of that, so I can say from here it is A plus B whole star, because you can take as many time any loop here, and then 1 2 3 A's, and then A plus B whole star, and then 1 2 3 B's, and then A plus B whole star. So this is the regular expression of this one. As we write, we are able to write the regular expression of this one. It means that NFA also represents regular language. Okay. So this is good. Now let's see this another uh, language here. It is also NFA. You see X1 does not take care of A here. No taking care of garbage collection, and it can accept 1 2 3 B's, or it can accept 1 and 2B. So this is a regular expression of that. So this is another NFA. So so now I have a question with you guys. Let me see who will give me the answer. Hmm. Nikhil, do you think that if I say that NFA is also a TG, is this a true statement or false statement?
I think an NFA is a type of TG, just not every TG is an NFA.
100% right. Perfect. So is not every FA is not equal to NFA. Every NFA is equal to TG. Every FA is equal to TG. Okay. Every TG is not equal to FA, every TG is not equal to NFA. Make sense? So now we go back one line which I said I will come back here. Look at this one. Every FA is NFA, whereas every NFA is TG. Okay? But every NFA is not FA. Exactly, every TG is not FA. The same way every NFA is not FA, because TG is relaxed version of FA. Exactly, NFA is a relaxed version of FA. So it has some, it follows something, it does not follow something. So now, if can I say that? So no, I already mentioned that every FA is NFA. So if you have an FA, so you can say that this is also NFA, this is also FA, this is also TG. So it meets all the requirements. Okay. So this is something you just see that. Every language that can be, so any confusion here, guys? No confusion? Okay. So now we are saying every language that can be defined by NFA can also be defined by deterministic FA. So what does it mean? It means that if you have a regular language, there must be minimum one regular expression of that language. There must be minimum one FA of that language. There must be minimum one NFA of that language. There must be minimum one TG of that language. It is not possible that we claim that this is a regular language and it is missing any one of this. It is not possible. It may have more than one regular expression, more than one FA, more than one NFA, more than one TG, but it is not possible that it is missing any one of this. It must have at least one of each of these things, okay, if it is a regular language. So now every language that can be defined by NFA can also be defined by DFA. So now DFA means your FA. It is same thing. Short name is FA. So every non-deterministic FA is a DG. So transition graph, you can convert that into regular expression. Regular expression, you can convert that FA. So it is interconvertible. So we can convert that into into FA. So now let's see one example here. I mean, this is the theory. So let's see one example here. So we have this. So this is our so we have this machine here. So, and this machine has this thing. It's a start state, and then it is B, it is X2, is B, is X3 or X4. Both are final states, then B and X4, and the final state. So this is your NFA. Yes. How we make it complete for FA? So make sure that you add a new state, which is a 5 state, and take care of garbage. B is taking care here. So take care of garbage collection. So B is going here. You need to add a new unique edge A here. B is going here, A here. B is going here, A here. B is going here, A here. A and B here, because after X4 you need A and B. And if you are here and you get another letter, so A and B here. Now you see we take care of garbage collection and we convert our NFA into FA by adding some more edges and some more states, and we make sure that now this new machine is taking care of garbage collection and it should be deterministic. So this way you can convert your NFA into FA. Good. Now we are saying that every language that can be defined by regular expression can also be defined by FA. So yeah, we know that it is possible. I just explained you. So proof by constructive algorithm starting from recursive definition of regular expression, we build an FA. Then by most recent theorem, it is possible to build a FA. So you can convert that. So now if you see this, more information. So NFA and Clean's theorem. So if you have an NFA and you want to apply Clean's theorem on that, so rule one, lambda and the letters in sigma. So now if you have a machine and you want to accept only one letter A on that machine and you want to draw an FA. So any one of you, do you think that this is valid FA? Lion, is this a valid FA? Which I just circle. Lion, are you there? Gunnar, is this a valid FA?
I don't think so.
Very nice. What are the problems you find here?
There's no transition for B.
Amazing. So it is not taking care of garbage collection. So you need, if you are here and you receive B, so it will not happen. It will be stuck. It will crash. So now this is not a valid FA. Besides, it is issued to make it valid. We need to do something like this. Let's say if we want to make this machine a valid FA, so what we need to do? We need to draw this and A here, and this is plus sign, and then another state, and B should go here, and A and B should come here, and the A and B should come here. Yes, now this is valid FA because it is taking care of garbage collection. And what is this FA it is doing? It is accepting only one word, which is A. That's it. It is, if you see, you are here and you give A, you go here. That's it. It is only accepting this word. If you give B or after that you do anything, it will not accept. So this is NFA. Okay, it is NFA, it is TG also. If you accept one letter B, it is like this. Lambda, it is like this. So these are the respective NFAs of these languages. If you want to apply R1 plus R2 in NFA, so you don't need to be, so you need to be, make sure that what I'm asking, am I asking you to find an R1 plus R2 for FA or NFA? If it is FA, you need to follow that long tedious path. If it is just NFA, then you have this machine one, this is your second machine. Just combine the start state of this machine with this one, and that's it. So one common start state, and this is your this machine, and then this is your this machine, and that's it. So combine with one common start state, and this will be your you convert your FA, your two machines you combine, make one machine, and this is your R1 plus R2 of NFA. Okay, it is not FA. And now, if you are interested to find R1, R2, you need to figure out that which one is R1, which one is R2. Let's say in this case, this one is R1, this one is R2. So start of this is this, and then final of this will combine with this. See, W2 and X1, and then and delete this final, because in this case when you have R1 R2, your word will be accepted when finish at R2, so its final will not be considered as final, and then you write this as it is and final will be here. So simply join the final state of the first machine with the start state of the second machine, and delete its final state and delete its start state. Delete this and that's it. Very simple. So you can get the R1 dot R2 of NFA. And whenever, oh, that's it. So we finish this chapter here. So guys, questions. I finished this chapter. If you have any questions, so please ask me question now.
I have a question, Professor.
Yes,
So
please.
for rule 3, in the combined graph, I just don't understand how on W2 there's a path of A going to X2 from W2. Can you just explain that real quick?
In this diagram which I open,
Yes, on rule 3, yes.
so it is, so when you have R1, R2, so you need to combine it here. Order matters, yes. All word will start with R1 and finish with R2. So when finish with R2, it means that you do not consider the final state of this machine, and start with R1, you do not consider the start state of R2. So you only consider final of this and start of this. So in this case, you need to make sure that which one is your R1, which one is your R2. Okay, because when you combine them, so any R1 or any R2 will not work. You need to know that which one is R1, which one is R2. So in our case, the first machine is R1, second machine is R2. So I write this state as it is. I write this state as it is. This is final state. I delete this final sign. I combine this after, because words start from here and then come here and then finish here. So then I combine this x1 here. I delete this start state sign, and then I write draw as it is, and I keep this final state. Now, if you see this, in this one new machine, whenever you give a word, this word will start from W1 and end with X3. So this is basically R1, R2. Start from regular expression 1, end with regular expression 2. So we simply combine the final state of the first R1 to the start state of the machine, and that's it.
I know, I guess I'm afraid of so between like W2 and X1, how did like you get like BA as a transition, or if you go from W2 to X2, you get A as a transition? Why B and A?
To okay, let me see what you're saying. Oh, okay. So you are saying that if you are at W2, this A is here, and if you have A, you go to X2, and if you have, if you see this, basically, what does it mean that if you are here and you receive A as input, uh, so you are not sure that this, so let's say I have a word, and this word is now something 3A's, yes, and I am at this state. When I combine this with this is, so it will be lambda, let's say. Okay, so then uh, if you are here and you receive A as input, so you are not sure that it is still here, or it it is this thing. Makes sense? Because this is a start state. So now, just to make sure, remember we have this scenario in somewhere in the previous example also. So just to make sure that whether it can handle here, because now you don't know that this A is on this machine, or so you reach here by 1A, and you are here now, and now this A will take you to here, and now you have two A's after that. So you are not sure that this two A's belongs to this, or it belongs to this, because this you connected that with this one. So that's the reason that it might be this or it might be that. So we have this A here, and A goes to X2 also. So see, if you are here, you go to X2. So we go to X2 also. But for W2 to X1, we need B, because this is a B here. So if you are here and you receive B as input, so it means you reach here. So this means this is your B here, which reaches to the X1. Because just say if you are here, if we do not have this machine, let's say, so I have a question. So if I have for only for this machine, if I have only this machine, can this machine accept word 1b if you are here? So is it possible that we can have this 3b's? Yes, we can have, because 1, 2, 3. It has a loop here. Yes. Now, to make sure that you can also get this thing, so you can 1b will reach you here, and after that, if it is your choice, you have more than 1b's or not, but 1b, you need 1b here to reach to here. So this is basically what. But I mean, I understand that this is not directly, but uh, we should, the way we created the two tables and this machine. I will ask you this kind of thing here, but this is just to show you that the how we connect that. But I mean, it should have a proper way of creating a tables, two tables, where you do not need to worry and think about this way. Just draw the machine according to the table, and it can draw this. But this is not in our scope at this time, at this level, undergrad level. So that's why they did not discuss in this book. Might be in master level somewhere they have proper. Behind that is that you need to combine the starts final state of this with the start state of this.
Thank you.
This any other question, guys? No question. So then I think that I published while you were in posting. So I already published. If you see, go to the modules. No, I didn't publish. I just chapter 8. But topics. Go to, we will finish this chapter, another chapter next class. Uh, be able to post. We will, if we finish chapter 8 in next class, so, it will. I will post. To solve that. So you finish those chapters. So you,
Professor, your microphone's cutting in and out. I can't understand what you're saying.
Okay. So I mean, we can hear what you're saying right now. It's a distortion or it's the loud noise, loud voice. Is this good?
It sounds like it's better now. It was just cutting in and out, like the internet was something.
Okay. I mean, weather is good. I didn't did anything. But now you are hearing, yes?
Yeah, it sounds good now.
Very good. So what I was saying that I will post assignment 2 today, and you will able to solve most of its questions. I believe there are only two questions which you are not able to solve, which is from chapter 8 and chapter 9. And so you can start working on that. And when we finish those chapters tomorrow, so then you can able to submit that assignment. And then if you finish this assignment this week, so then I will post the solution of assignment 1 and assignment 2. I already posted the solution of quiz 1, quiz 2, quiz 3. And then quiz 3 I didn't, because there was one guy, he has to attempt the quiz. So I'm waiting for that. If once he attempts, so then I can post that. So then, I mean, we will have, once you done your assignment 2, so then we will choose any day next week. I prefer it should be the class time. So during this class time, you can you can use that time for the exam, for which will be from chapter 1 to chapter 9. So then we done the half course. Okay. So this is my plan. And then we finish the next half, and the next final exam will be, it will not be the comprehensive exam. It will be from chapter 10 to onward chapters, I believe chapter 19. So that will be your final exam from the remaining part of the course. And you will expect two more assignments and few more quizzes, and then job will be done. Okay. So if you have any questions, so but I have this feeling, you guys, do you guys know how to access the office hour meeting?
Isn't it the same as how you get into this meeting?
No, 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 no. It's not the same. I am very, because from the last 3 weeks, always I wait 1 hour and I don't go anywhere. The way I'm sitting here, I keep sitting here for 1 hour and doing nothing, and nobody show up. I am suspicious that might be you know or you don't know. So now let me show you that how to access the office hours. I mean, nobody send me any email that they try and it is not working. So I guess that nobody tried that. So if you go to your course home page, so you guys see my screen. So here you see office hours: Monday, Wednesday, Thursday, 11 a.m. to 12 p.m. What is this today? Today is Wednesday. Oh, today, yeah, we have office hours. So you can click here, this thing, and this will take you to another meeting. So this is my personal. So you start meeting here. So I don't know how it will look like on your side. So you need to click on this one. This will start another WebEx meeting. So I keep it separate because I don't want to be merged this with the class meetings and all that stuff. So this is a separate link. And once my class time finish, I always go to this link, and I wait for you for 1 hour. Nobody show up. So, but I mean, it is not mandatory that you have to show up, but I mean, if you have questions, so please use this time. uh, I should be your main source of information. Please do not rely on your fellows. I don't mean that they don't know, but please don't struggle. If you have me there, why you struggling and finding the information and exchanging the information with each other? So use me. I'm here for you. So I dedicatedly always sit 1 hour. I am available by email. I'm available by appointment. Any other time you are working an assignment, please do not struggle. Send me email. I will right away come to the office hour meeting link. And instead of sending me email and writing long stories there, It is very quick if we talk, you talk, I talk. I feel more comfortable by speaking than writing an email. Sometimes topic is so complex, it is not possible to explain by writing. So it is more worth that we talk face to online or this way. So please use office hours if you are struggling with um, any of your assignment or question. Okay. Okay, guys. I think we should stop here. I am stopping this recording now.